Hello everyone. In this video we're going to be solving a nice number theory problem. So we have a factorial equation and an exponential function on the right hand side. And we're going to be solving for integer solutions, but we're also going to talk about the real case. I'm going to show you a couple graphs. So n factorial equals 2 to the power n, and I'm pretty sure you were able to guess at least one of the solutions. But let's go ahead and take a deeper look. First of all, I want to show you for real n values what the graph of n factorial, or you can call it f of x equals x factorial, going to look like. So this is what it looks like according to Desmos. And that's pretty interesting because this can be defined using the gamma function. You know, there's a way to define it for all real numbers pretty much. Okay, it's a very curvy graph, and then think about how this would interact with an exponential function. At the end, I'm going to show you two more graphs, which is going to make it hopefully a little more clear. All right, great. Let's go ahead and get to the solution. So first of all, notice that we have n factorial equals 2 to the power n, and we're looking for integer solutions. Now, if n is greater than 2, as you know, then n factorial is going to contain at least 1 3. And obviously, that is not going to be a power of 2. Because in order to get a power of 2, they all have to be 2's, right, being multiplied. So in other words, this is not going to work if n is greater than 2. So n must be less than or equal to 2. And here I have 3 values that I need to test. Since I'm not going to deal with negative integers, you could also look at that. I don't think there's a negative integer solution, but I could be wrong. You can check it out. N equals 0, n equals 1, and n equals 2. 2 is included because 2 is obviously contains a single 2. Okay, if n is equal to 0, let's go ahead and plug it in on both sides. Does 0 factorial equal to 2 to the power 0? That's a question mark, right? And as you know, this means 1 equals 1, and that's actually a check. Okay, great. So for n equals 0 works. Let's go ahead and circle it and then continue. For n equals 1, we get 1 factorial equals 2 to the power 1. Does 1 equal 2? The answer is no. So this is not going to work. Cross it out. N equals 2. For n equals 2, we get 2 factorial equals 2 to the power 2. But 2 does not equal 4, is it? Again, I forgot to put a question mark. That's false. Okay, so we're going to discard this as well. So the only solution we get from here is n equals 0. Okay, there's also another good reason why we're not going to get solutions when n is larger, because if you think about it, if n is greater than or equal to 4, then n factorial is going to be greater than 2 to the power n. Think about n equals 4. That's 4 factorial, which is 24. 2 to the 4th power is 16. For example, for n equals 3, if you take a look at it, 3 factorial is 6, and 2 to the 3rd power is 8. So the power is larger than the factorial. Okay? But as soon as you hit 4, you're going to notice that the factorial is going to get bigger and bigger. So I'm going to go ahead and show you a table, kind of like we'll make a table, and I'll kind of show you what that looks like. So we're going to have 3 columns. We're going to have n factorial and 2 to the power n to be able to compare these values. We already know the smaller values, so let's go ahead and use some larger values. How about using 3, 4, 5, 6, and 7? For 3, we have 3 factorial, which is 6. We have 24, 120, 720, and 5040. As you can see, they get bigger and bigger. And for powers, we have 8, 16, 32, 64, and 128. Obviously, the factorial is going to grow faster, and you notice that in this case, n factorial is going to be greater than 2 to the power n. But we could also prove this by induction. Let's go ahead and take a look at it before we start talking about the real solutions. Okay? So we said that my claim is n factorial is greater than 2 to the n for n values that are greater or equal to 4. So proof by induction basically works in 3 steps. First step is the base case. Second step is the assumption for n equals k. And then the third step just demonstrates if something is true for n equals k, that implies it's truth for n equals k plus 1. Make sense? I hope it's rigorous enough. I know some people are going to find this not rigorous enough, but anyways. So first step is going to be for n equals 4, basically, we're going to get 4 factorial, like I said earlier, which is 24, which is greater than 2 to the 4th power. So this is my base case, okay? This is true. And I claim that n is greater than or equal to 4, so I'll test the smallest value for my base case. And then for second step, I'm going to assume for n equals k that this statement is true, which is k factorial is greater than 2 to the power k. So this is an assumption you must make. And then the third step should show that this implies, so if you call this p sub k, we have to show in the third step that p sub k implies p sub k plus 1. So for k equals 4, this is true. That implies p of p sub 5, and then p sub 5 implies p sub 6, so on and so forth. Make sense? So we get kind of like get a chain of truth values. Anyway, so how do you go from this statement to p sub k plus 1? Let's go ahead and take a look. So first of all, we're going to start with k factorial is greater than 2 to the power k. Okay? I left some space there so I can multiply by something. Now I'm going to go ahead and multiply both sides by k plus 1. So we start with k factorial is greater than 2 to the k, and we multiply both sides by k plus 1. We can do that, right? Okay, since k plus 1 is a positive quantity because k is greater than or equal to 4. Now what does this give me, right? It kind of gives me something like this. K factorial multiplied by k plus 1 gives me k plus 1 factorial. So okay, I got part of it. And then on the right hand side, I got this. But I kind of need to show that this is, actually the left hand side is greater than 2 to the power k plus 1. But if you take a look at it carefully, you're going to notice that if k is greater or equal to 4, then k plus 1 is going to be greater than 2, right? So we can basically show the following. We can take this and multiply both sides of this by 2 to the power k. So it's going to be 2 to the power k times k plus 1 is going to be 2 to the power k times 2, which is 2 to the power k plus 1. This just shows that this expression here is greater than 2 to the power k plus 1, and that is exactly what we have here. So this implies that this expression right here is greater than 2 to the power k plus 1, and by a chain of inequalities or using the transitive property, this basically gives us the following. K plus 1 factorial is greater than 2 to the power k plus 1, which is actually a result that is obtained by this assumption. So p sub k implies p sub k plus 1. In other words, if k factorial is greater than 2 to the k, this implies that k plus 1 factorial is greater than 2 to the power k plus 1. And then this completes the proof. Okay, great. So we basically get the expression, and this means for all n greater than or equal to 4, n factorial is greater than 2 to the power n. Therefore, there's not going to be any other solutions when n is far out. Okay, great. So let's go ahead and take a look at two graphs. We found n equals 0 as the only solution. As you can see in this graph, that happens to be an intersection point. But there's also another value for which this is true, but that's a real number, not an integer. Why is it true? Can we solve to find it? Probably not, but anyways. I'll be looking forward to your comments. And this is just a graph from Wolfram Alpha, which is a little distorted, but sometimes it's better if you don't want to zoom out like crazy. And as you can see here, the gamma function is mentioned. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.